So, have you ever had problems with crosstalk? When I was starting with hardware design, my very first problem, which I had no clue what is happening on my board, was crosstalk. Basically, the microcontroller on the board was receiving some interrupt requests which were never happening. And then I designed another board where I had a lot of problems with crosstalk. It was a two-layer PCB where I routed a lot of tracks close to each other, and the board was sometimes freezing and crashing and resetting, and I had no idea what is happening. And I have seen so many PCBs which are routed this way, and I still see people routing two-layer PCBs with tracks which are just every single track is close to the other one. And I believe it's like super important to understand at least a little bit about crosstalk. So I decided to create a video about this topic. And I was talking to Eric Bogatin, and he has like a really cool animation which explains when crosstalk happen and what exactly it is. And when you will see this animation, you will be like, oh, so this is how crosstalk appears on my boards. And that's basically what we are going to talk about. So in this video, I'm going to talk to Eric Bogatin. We had a call which I recorded. In this call, Eric is going to initially explain a little bit what is behind the theory of crosstalk, and then also he will play this animation and explain actually what crosstalk is. My name is Robert Feranek, I'm from Fedevel Academy. I really hope you will find this video interesting and useful. Here it is. Here is the video from my call with Eric Bogatin.
So fundamentally, crosstalk is all about electric and magnetic fields. And when we talk about crosstalk, there's always one or multiple signal and return paths that are the aggressor that are causing the noise, and there's a victim on which we see that noise. The fundamental root cause for all crosstalk is always a combination of fringe electric fields between the signal and the aggressor and the victim, and fringe magnetic fields. And if all the, if you put a signal on the signal and the return, if all the electric fields were confined in the vicinity of the signal and return, so none of them spread out, there would be no crosstalk. And we call these fields that spread out, we call them fringe fields. And so crosstalk is all about fringe electric and fringe magnetic fields. You need a lot of math to understand electric and magnetic fields. And in fact, if you want to do a practical problem, gosh, it's really hard to, get a paper and pencil and Maxwell's equations and write down equations, solve the differential equations, get the fields and do something with them. And so we approximate the behavior of electric and magnetic fields with circuit elements. But keep in mind that the real way the world works, the real effects that are going on is related to the fields. We're only approximating that behavior with circuit elements. And how do we approximate the electric field coupling? Do you know what the circuit element that approximates how electric fields couple onto?
It's capacitor, I
It's
believe.
capacitors, right?
I'm right.
Yes, exactly right. Yeah, you have that very good intuition. And likewise, if we have fringe magnetic fields from one signal return path over here to a victim line over here, it's the magnetic fields.
It will be inductor.
It's inductor, right? Mutual inductance, right? And so when we describe crosstalk, we will sometimes approximate the electric field coupling with a capacitive coupling and the magnetic field coupling with inductive coupling. So those are the words that connect those fields. But just looking at the field lines, if you imagine, and so the other important principle is how how do you get crosstalk through electric fields? I mean, here's this electric field from the signal and return over here, and it's going to the victim line. How does the electric field couple anything over to the victim line? Well, if you think of it capacitively, then how do you get current? If we approximate an electric field as a little capacitor, how do you get current through a capacitor?
Because
what's the only way?
There are different voltages.
More than just different.
Or field.
I mean, and the different voltage gives you fields, but even if you have a constant voltage across a capacitor, there's no current flowing through the capacitor. What does it take in order to get current through, get energy flowing through a capacitor?
Change.
A change, right. And so it's the changing electric fields that, if it's modeled as a capacitor, the changing voltage across the capacitor, that you get capacity coupled currents as a form of crosstalk.
I feel like I have the exam.
It is an oral exam, but you know what? You have very good intuition about this, and so I have high confidence you're going to get everything correct. And here's how to think about, and this is one of the most important concepts in the electric field perspective for crosstalk. I have these electric field lines that I've drawn between the aggressor and the victim line. We approximate them by capacitance, but as electric field lines, when I have a changing voltage, it's the voltage difference that gives me the field lines. But if that voltage difference changes, the electric field changes, and a changing electric field is equivalent to a current. We're used to thinking about current as little moving charges in a conductor. That's conduction current. That's the electrons moving in copper. But there's another kind of current as well, and that's a changing electric field. And that's how you get current through a capacitor, because in a capacitor, remember, there are two conductors, insulating dielectric. You don't have little charges moving through the insulating dielectric. So how do you get current through a capacitor? It's because of the changing voltage, which means a changing electric field. And we call, actually, it was James Clerk Maxwell that named that new kind of current that flows through the electric field lines when those electric field lines change.
It's called, is it the displacement current?
Exactly. You see, you are on a roll.
I watched my video.
Right. Yeah, it is displacement current. And so here's what you need to do. You need to visualize, when you look at the electric field lines, you need to visualize those electric field lines, because when they change, when the voltage changes, you're going to have, it's not really charges, but it's still a current flowing through those field lines from the aggressor to the victim, and we call that displacement current. And it is just as real and behaves exactly the same way as conduction current, even though it's through space, literally through space or through dielectric. So whenever you see electric field lines, you're going to get displacement current when the field lines change, when the voltage changes. And likewise with magnetic fields, you can have static magnetic fields when there's a constant current. When do we get induced voltage on the victim line from the magnetic field lines?
Only when it is changing.
Only when the magnetic field lines change, and they change because of a changing current. Exactly right. And so it's the changing rings of magnetic field lines, the changing number of rings of field lines that surround the signal path, the victim line. It's when those rings of field lines change that we get induced voltage. Then induced voltage drives a current down the line. So it's the magnetic fields, and how many of these rings of magnetic fields go around the victim line is a measure of how much inductive coupling, how much magnetic field coupling. And so just thinking about it in terms of the fields, if we want to reduce the crosstalk, we want to reduce the number of field lines that go between the aggressor and the victim, electric field and magnetic fields. And there are two ways we can engineer the interconnects to reduce the number of electric field lines and magnetic field lines between the aggressor and the victim. What is one of those ways? Physically, how can we move it away? Exactly right. So we can pull the aggressor, the victim away from the aggressor, reduces the number of fringe electric fields, reduces the number of fringe magnetic fields, and that reduces crosstalk. There's another way as well.
We could move the reference plane closer.
And what would that do? You're right. Move the reference plane closer. And what would that do?
Reduce the fields, make them a little bit smaller.
What we do by adjusting the return plane is we sculpt those fringe field lines. By bringing the return plane closer, we confine the fringe electric field lines closer to the vicinity of the aggressor. They don't spread out as much. And same thing with magnetic field lines. If we bring the return path closer, we constrict those rings of field lines. Fewer of them go around the victim line, and we reduce the magnetic field coupling or the inductive coupling.
I'm going to interrupt Eric because there is something super important what I would like to point out. Notice in these examples, we always have this reference plane. What does it mean, a reference plane? For example, in your PCB, what can be usually a really good reference plane? Nice and solid ground plane. So, for example, when you are routing a PCB, then you would like to have tracks on one layer, and then on the other layer, maybe you would like to have this nice and solid ground plane, because that's the situation what we can see here. Because this nice and solid ground plane can help us, for example, control these fields. If we move the ground plane further from the tracks, then the fields are going to be bigger. And when we move this ground plane closer under our tracks, then these fields are going to be smaller. Now the question is, what about two-layer PCB? If you are like very lucky, you may be able to route all the tracks on the top layer of two-layer PCB, and you may be able to create nice solid ground plane on the bottom layer of two-layer PCB. However, the distance between top layer and bottom layer on two-layer PCB is huge. And even if you would have this nice solid ground plane on two-layer PCB, these fields are going to be very large. In reality, there is almost never a way to create nice solid ground plane in two-layer PCB. In reality, usually there is no nice reference plane on two-layer PCB. So if we remove this reference plane from this picture, what is going to happen with these fields? They are going to spread all around. These fields are going to be picked up with all the other traces on your PCB. So that's one of the reasons why two-layer PCBs are so bad. Because you cannot have this nice solid ground plane which can help you, for example, to control these fields. Okay, I wanted to point out this because when we talk about these pictures, we use always this reference plane, and I wanted everyone to be aware that this, what we are talking about, it applies only in these situations when there is this reference plane. If there is no reference plane, everything is going to be much, much worse. Okay, let's go back to our talk with Eric, and let's listen what Eric is going to say next. Here it is.
Here's an example of dynamically how that crosstalk looks. So here's what I've got. And I've kind of exaggerated the drawing a little bit, but here's a trace on a board, aggressor. Here's a trace on a board, a victim line. Here's the return plane. And I've kind of, hand drawn in. Here's the capacitance between the signal and the return. And here's that coupling capacitance. And you got to imagine that the fringe fields between the aggressor and the victim, they're creating this distributed capacitive coupling all the way down the line. We're just looking at, one little region over here and the capacitive coupling between it, right? So here's that edge, and I've drawn this purposely in an example showing what I would call an electrically long interconnect. Electrically long meaning that the rise time is short compared to the physical length of the interconnect. So example, I get a nanosecond edge, then electrically long is, like 6 inches, because the edge is moving at 6 inches a nanosecond. Nanosecond long, its spatial extent is about 6 inches in extent. So if it's shorter rise time, then it'll be a smaller spatial extent. And that just makes it easy to think about this crosstalk from an aggressor to a victim. And so here's this edge moving by. When do I get the noise flowing between the aggressor and the victim through the coupling capacitance? When is the only instant of time that I'm going to have noise flowing from an aggressor to a victim through the coupling capacitance?
When the change is happening.
When the change happens, exactly right. So at this instant of time right now, here's where the edge is, here's the capacitor. I'm not getting anything flowing through here. It's only when this edge passes by this region that I'm going to get that capacitor coupled current flowing from the aggressor to the victim. And as soon as I get that dV/dt across the changing voltage across the capacitor, and I get that burst of displacement current through the capacitor, and it comes over here and it's now on the victim line, I get capacitance between the signal and the return of the victim line. That current flown over is going to build up some charge here. I'm going to get a voltage. Now I've got a voltage pulse, a voltage signal appearing on the signal and return of the victim line. What's that voltage pulse going to do?
It will travel with the edge.
It will travel. It will propagate. Exactly. And which way will it go? Will it go in the forward direction, the same direction the signal's moving, or will it go in the backward direction, the opposite direction?
It looks like for capacitance, it will go both directions.
Yes, it will split because it's just a voltage pulse. It's like you added a little voltage source between the signal and the return, and so it's going to go in both directions. And that voltage from the capacitor coupled current is going to travel signal return in one direction, signal return in the other direction. And so we're going to get it at this end, and just to distinguish the direction. So here's this case here. I should have gotten my directions right. So I've got this pulse. It's moving down this way, down the aggressor line.
Yeah, I noticed that. Yeah.
Yeah. And so here's where we get the dI/dt or the dV/dt. We get the current in here. We get some of the signal return current going in this direction, some in this direction. To describe this direction or that direction, we refer to the source, where the signal's coming from on the aggressor. We call that the source. That becomes the forward direction. And this is the forward direction of the current. This is the backward direction.
Mm-hmm.
Or because this is also where the source is, this direction is toward the near end of the source, and this direction on the victim line is the far end, far from the source. So we use those terms interchangeably, backward or near, forward or far. So the capacitively coupled current is going to flow between the signal and return. It's a voltage pulse. It's signal return in the backward direction, signal return in the forward direction. That's the capacitively coupled current. And so we'll see it eventually when it gets to the near end. And as it propagates in the forward direction, the aggressor is moving in the forward direction, and so they're kind of coincident with each other. And so in the backward direction, I get this little bit of capacitively coupled current that's going to dribble back to me. The aggressor is going to move forward. We're going to get capacitively coupled current. It's going to dribble back, moves forward, get a little bit more dribbling back. And if I sit over here at the near end, I'm going to see this capacitively coupled current kind of dribbling back, dribbling back, dribbling back. Now it's a little hard to visualize. It's a very much a dynamic kind of thing. Really hard to visualize on this flat screen and just moving my mouse. And so I've got this really cool animation that shows how this capacitively coupled current behaves. But this is the principle. You get displacement current going to the quiet line. That builds up some charge, makes a voltage. That voltage signal propagates. You get current, signal return, current loop going in the backward direction, signal return in the forward direction. So here is the animation. So this was done by one of my buddies at Telenicroy, Yoshi Tetsui. He is an ace at writing flash animation. And he developed this flash animation to describe crosstalk. And so here's what we've got. Here's a aggressor line. Here's a victim line. And here is the region in which they're coupled. And I can change that region, make it big, and I can make it short. So make it really small. Just a small region in which they're getting close together. Normally they're far apart. They get close together here and they move apart. So they're only coupled in this little region here. And so I have this we're going to look at capacitively coupled current first. I have this capacitive coupling between the aggressor and the victim line here. And I'm going to send a signal down. We look at the edge of that signal. And this is going to be a plot of the voltage versus position as we send it down. And it's in this region that I'm going to get capacitively coupled noise. And once it gets over here, it's going to propagate in the backward direction and the forward direction. And we'll look at that voltage that propagates. Okay, so that's the setup. And I'm going to use a strip line. So the capacitive and inductive coupling are the same. So let's run that animation. Oh, I'm sorry, I need to do that. Here it is. So here's that edge. It hits the coupled region. And when we hit that coupled region, we get a little bit of capacitive coupled voltage moving that way, a little bit moving that way. Okay, so let me see if I can slow it down a little bit. So here's that. It's only, look, we're not getting anything, nothing, only where the edge is. And after the edge is passed by, nothing. We get a burst of crosstalk moving in the backward direction and the forward direction. Equal amount. They're both positive because it's that voltage that that drives the signal return in both directions the same amount. If I increase the coupled region, then I'm going to have that same burst generated where I have that little bit of coupling capacitance, and then another region, another region, another region. Every place where that edge encounters that capacitor is going to generate a little bit of backward going noise and forward going noise. But as the backward going noise propagates in the backward direction, the aggressor is moving forward, it's encountering a new region, and we get another amount of backward going noise.
So it will increase?
It will dribble back. In the forward direction, as I get my little bursts of capacitive coupled current in the forward direction, it moves forward, the signal moves forward, and that's where it's going to snowball. So let's watch it now. So I've gotten a little bit more capacitive coupling here. Let's look and see. So here's this region. So the edge encounters the region. I get a little bit. Look, I get it dribbles back, but they're all on top of each other in the forward direction. And so the signature of the noise we see on the victim line looks different when we look at the noise propagating in the backward direction, what we see over here at the near end, versus in the forward direction that we see over here at the far end. So let's do that again. So you can see the backward going noise, here it is. It's dribbling back. It looks like a constant steady amount. In the forward direction, they're being generated coincident with each other, on top of each other. As the aggressor moves, it gets bigger and bigger, the more the coupled region, until it all comes out and we get a big amount. Let's watch that.
And I think for people, we can say the coupling region is basically the region which we consider that when the tracks influence each other. Outside of the coupling region, there is no influence between them.
Right, they're far apart. They come together because they're necking down, and then they're pulling apart. So this is the region when they're close together. And now I've made it really long. And now we look at the capacitive coupled current, and we're going to get a steady amount of current generator voltage signal going back, dribbling back. And look, it's this constant steady amount. Even though we're increasing the coupled region, we're not increasing the amount, the magnitude of the near end crosstalk. We're increasing how long it lasts, but not the magnitude. Whereas the forward direction, look what happens. The longer the coupled region, the more opportunity we have for that far noise to get bigger and bigger, and it's just growing. We get a large pulse coming out. Very different signature in the backward direction than in the forward direction.
But is it going to grow forever?
No, but it will grow so that the magnitude of the far end noise could be comparable to half of the signal. And long before it gets that big, the technical term for that situation is you're screwed. Because as that far end noise grows, it's going to get, here it is, it's going to get bigger and bigger. And at some point, that's going to be big enough to cause real problems. And it will get big enough to cause problems way before it saturates. And so that's why far end crosstalk, when it happens, can be much more important than near end crosstalk because it can be so much larger. But
so you say half of the signal, that's
it can
the
grow
maximum.
as large as half of the signal, right?
Okay.
But we're only looking at half of the far end crosstalk because we only looked at the capacitively coupled current. I said that when you have the nice wide plane, the relative amount of capacitive and inductively coupled current are comparable. They're both important. We have to worry about both. But here's where the subtlety comes in.
I would like to ask, why is it half?
Yeah. So imagine so going back to this drawing here, as the signal is moving forward, the energy that's coupling from the aggressor to the victim and is building up and getting bigger and bigger in the victim line, where's that coming from? Where's that energy coming from that's moving down the victim line?
Okay, it will be half because it kind of splits between these two.
Yeah, so it's gonna come from the aggressor, and so that means we're going to distort the edge of the aggressor. If we get so much far end crosstalk that it becomes close to half the magnitude of the signal line over here, that means we have taken so much energy out of the aggressor line that we've distorted this edge, and now that same edge that is half the voltage over here, that's the same magnitude that I have flowing this way. It's going to act like an aggressor and it's going to go over. And so they equilibrate roughly to like a half, roughly. But long before that happens, you're screwed because you have so much far end crosstalk here, it's going to look like a bit error. But that's only half of the crosstalk. It's only capacitive coupling. Now we have to look at inductive coupling. So here's this edge, and here's some mutual inductance between an aggressor and a victim. So this is where it's really, gosh, it's really hard to conceptualize what goes on here. This is where understanding electric and magnetic fields is really valuable because we have a loop here, a signal return loop for the aggressor, and we have a loop here, a signal return for the victim. If I have a constant current, there's no change in magnetic field, there's nothing induced. When I have zero current, there's no change in magnetic field, there's nothing induced. It's only when I have that changing, that edge, I have that changing current in the rise time on the aggressor where I have a dIdt over here, a changing magnetic field, and that generates the changing voltage over here, and that generates a changing a current over here. And here's where the very, very, very subtle part comes in. Suppose that my current increases this way in the counterclockwise direction, because here's this edge, the current gets bigger and bigger and bigger, increasing in the counterclockwise direction right over here. That's going to generate a changing voltage over here, and that's going to, in this victim loop, and that's going to generate an induced current. And now comes the very subtle question. If I have a dIdt increasing in the clockwise, this is the counterclockwise direction in the aggressor, what's the direction of the induced current loop in the victim? Is it going to be increasing in the same direction or in the opposite direction? So I get an aggressor loop increasing in the counterclockwise direction over here, generating changing magnetic fields, generates changing voltage, generates changing current. Is the induced current going to be going in the same direction, circulating in the same direction, or circulating in the opposite direction?
I guess it's the arrow there.
Huh?
Is it the arrow there?
It is. I kind of gave you the answer. Okay, so here's this edge moving down. You get an aggressor current increasing circulating in the counterclockwise direction. It's still propagating in the forward direction, just circulating in the counterclockwise direction. And now over here in the poor victim line, the edge goes by. We get mutual inductance in this region. We're going to get a clockwise induced circulating current loop over here. And now comes the second really subtle point. What direction is that induced current loop in the quiet line? What direction is that loop going to propagate? Is it going to propagate this way and be a signal return, signal return, signal return? Or is it going to propagate this way and be a return signal, return signal, return signal? Which way will it propagate? This loop of current that was just excited is going to propagate in the backward direction and the forward direction. And when it goes in the backward direction, it's going to be a signal return, signal return, signal return, just like the capacitive coupled current. You're going to be exactly, there's going to be a little positive burst of voltage moving in the backward direction from the inductively coupled current. In the forward direction, it's going to be a return signal, a return signal, a return signal, a return signal. And if signal return is a positive voltage, what kind of voltage signature is a return signal direction of circulation, it's going to be a negative voltage. And so in the forward direction, we have a positive voltage burst that's moving back. And in the forward direction, we have a negative voltage pulse moving in the forward direction from the inductively coupled current. And again, really hard to visualize.
Let's see
and that's
the
where
animation.
the animation comes in, right? So I'm going
Because
to go back to...
I've got lost.
Yeah, it's unless you have looked, this is where thinking about magnetic field lines and how the induced current is really valuable. So here's that very short coupling region, and here's that edge that's going to come by. We have just a very narrow region in which they're coupled, and we're going to look, instead of the capacity coupled current, we're going to look at the inductively coupled current. And so what we expect to see is nothing, nothing, nothing until the edge gets over here. We have a signal return circulating in this orientation here. We're propagating this way. It's circulating in the clockwise direction. The induced current, inductively coupled current in the quiet line, is going to be going the opposite direction. That's Lenz's law. And we're going to get half of it moving in the forward direction, half of it moving in the backward, half of it moving in the backward direction, half of it moving in the forward direction. And so that's going to be a signal return, signal return, signal return, moving backwards. That's a positive voltage. And it's going to be a return signal, return signal, return signal, return signal, negative voltage in the forward direction. So let's watch that. So here's that edge, nothing, nothing, nothing. Here we get that little positive positive inductively coupled current moving in the backward direction, and we get that little negative burst of voltage moving in the forward direction. And so once again, we see a very different signature in the backward direction as the forward direction for inductively coupled current. Remember what it was for capacitive coupling. It was both positive in both directions, right? But for inductive coupling, it's positive in the backward, negative in the forward direction. And if we increase the coupled region, the behavior, the signature is going to be exactly what we saw for capacitive coupling. Let's make this a little bit bigger. So let's look at that inductive coupling. So it's going to be, we get that little positive burst, and it's going to be dribbling back, dribbling back, dribbling back, dribbling back. The forward direction, it gets bigger and bigger. It's snowballing, gets bigger and bigger, more negative. And if I make it really big, again, we're only looking at the inductively coupled noise. If we make it really big, we're going to see in the backward direction, in the near end, when we're sitting over here, a constant steady amount lasting for some amount of time, the round trip time, constant steady amount independent of the coupling length. But in the forward direction, oh my gosh, it got bigger and bigger and bigger and bigger, and we get this large burst coming out coincident with when the edge
But
comes
now
out.
I'm going to be really confused because it looks like it's going to eliminate each other.
What an astute observation. You are exactly right. If the capacitive coupled noise and the inductively coupled noise are of the same magnitude, then they're going to cancel out in the forward direction. Let's take a look at that. Let's do one section. Now we're going to look at both. So we looked at capacitive, we looked at inductive. Now we're going to look at the total. And so we're going to have the capacitively coupled noise in the forward direction. Here it is in red, and the green is the inductively coupled noise, both the same magnitude, and we get twice the amount. In the forward direction, wait a minute, what happened? What happened in the forward direction? We get a little bit of positive capacitively coupled current. We get a little bit of negative inductively coupled current. They're exactly canceling out. There's nothing in the forward direction. And in fact, if we make it really long coupling region, then the capacitively and inductively coupled current will dribble back, dribble back, dribble back, dribble back. But the capacitive and inductive couple in the forward direction get bigger and bigger, but they're exactly the same. They cancel out. There is no far end crosstalk.
Okay, and now you know. Now there is this question. Then why we are talking about crosstalk?
Because, well, number one, we have near end crosstalk, and near end crosstalk is a problem. And this is in the special case of a strip line. When I have two planes and I have nice homogeneous material in between, so in the stack up, I get the same dielectric, above and below, say material above and below. In that environment, the inductive and capacitive coupling are the same. They're opposite sign. They cancel out. No foreign crosstalk.
Okay,
but we
so
still have, but we're not
ideally
done.
you would like to route all the traces between two grounds. Yeah.
If we care about foreign crosstalk, and if you want to eliminate foreign crosstalk, you are exactly right. You want to use strip line geometry.
But then the distance needs to be kind of same from the planes, no?
The only thing that's important is you get the same dielectric material above and below.
Okay.
Which is normally, you have a core and you have prepeg. They're close. They're very close. And so you'll mostly eliminate foreign crosstalk. If we don't have that, if we have a microstrip, because you always have surface traces. And if you look at a lot of especially 4-layer boards, you'll find long parallel buses routed in the microstrip traces that are really close together. So here's the case, doing the same analysis with microstrip. The only difference is the relative amount of capacitive and inductive coupling. I'm going to make our coupling region really short. So in this environment, there's going to be a little bit more inductive coupling than capacitive coupling. And so here's the capacitive coupling. And we get a little positive burst, just like we saw before. Here's the inductive coupling. We're going to get a little positive burst going in the backward direction, negative in the forward direction. But the capacitive and inductive coupled noise, not quite the same. There's a little bit more inductive coupling. So when we look at the total, they don't cancel out. They add in the forward direction, so I get more. They don't quite cancel out in the forward direction. And that means that when I have a long coupled region, I'm going to have in microstrip surface traces where I have more inductive coupling. The inductive coupling is larger. I have a net negative voltage in far end. So in microstrip, far end can be large. It scales with length. So the longer the coupling length, the region, the more the far end cross, and it scales inversely with rise time.
Is it going to be again like maximum half voltage, or
yeah, but again, long before then, you're screwed. Long before the far end crosstalk is half the signal, you've got so much noise that now you're getting false triggering.
And why this is happening? Is it because half of the environment is air and the other one is PCB?
In that environment, so one of the things you learn when you take a fields class is electric fields interact with dielectrics. Right? There's the dielectric constant, tells you how much is the electric field in the material kind of amplified a little bit by the dielectric. Magnetic fields, on the other hand, don't interact with dielectrics at all. And so whether I have in strip line or microstrip, regardless of what my distribution of dielectric is, I don't change the magnetic fields. The magnetic field coupling is the same. But when I add when I take away the dielectric above the signal lines to go from strip line, so here's the strip line, I have dielectric up above. If the electric and magnetic field coupling, capacitive and inductive coupling, is the same in this environment, and I take away the top dielectric, what's happened to the magnetic fields and the magnetic field coupling? Nothing. They're not affected by the presence of the dielectric. So in this environment, I have exactly the same magnetic field coupling between these as in this environment. So inductive coupling stays the same. But when I had the dielectric up above here, what happens to, remember, the capacitive coupling is all about these fringe field lines. When I have the dielectric up here, I have extra coupling between these fringe field lines because of the dielectric. They've kind of amplified the electric field a little bit. And so I have a lot of electric field coupling that makes the capacitive inductive coupling comparable amount. When I take the dielectric away and I look at microstrip, those same field lines, they don't have the dielectric here. I have less coupling. So here's the counterintuitive principle. I decreased the capacitive coupling, and yet I've increased the far end crosstalk because I've made the capacitive and the inductive coupling not equal anymore. They're not canceling each other out. By decreasing the capacitive coupling, I've actually increased the far end crosstalk because I don't have that capacitance to cancel out the inductance. And that's why it's the inhomogeneity of the dielectric material, the fact I have air and dielectric here, that gives a different amount of coupling capacitive and inductive. And that's why we have far end crosstalk.
Okay.
And so we have these two behaviors, something different at the near end versus the far end. And that's why we call it near end crosstalk and far end crosstalk, to distinguish those.
This is very interesting because when I was thinking about making this call, I imagined the like standard pulse and then, you know, some ringing or something. And I was like, oh, this is the crosstalk, what we can see on the other victim. And I was not really thinking about crosstalk this way. So thank you very much.
There are two things that complicate this simple analysis. This is exactly what happens. This is the coupling. This is what you measure. I do this in my class quite a bit. We build coupled transmission lines. We send a SEP edge in. We look at the near and far and crosstalk. Looks like this. Two things that make it a little more complicated. On the victim line, I've just introduced this pulse. Remember, when we sent the signal in, we get this signal on this is on the aggressor. We get this signal on the victim line. The victim line doesn't know it's a victim line, doesn't know this is crosstalk noise. It thinks this is signal, and it's going to interact with the terminations at the ends exactly the same way a signal would interact. If I have an open here, far end crosstalk is going to reflect here, and it's going to bounce over here, and it's going to bounce back and forth. The near end crosstalk is going to bounce back and forth. So the terminations on the victim line influence how that noise rattles.
So termination will make the ring.
Will make some ringing, and the termination on the aggressor will make the ringing. And if I have an open over here, like source series termination, for example, if I have an open at the far end of the aggressor, the signal is going to go this way. I'm going to get the near and far and crosstalk over here. It's going to reflect, and now this is going to be the forward direction, and I'm going to have far end crosstalk over here at the receiver and near end crosstalk over here that may reflect. And so the multiple reflections in the aggressor and the multiple reflections in the victim are going to make the signature look a little more complicated.
So that's why if your lines and output and input, if they meet the required impedance, it makes it much better because you kind of stick with this one simple example, simply to say, but you eliminate all the other possible crosstalk which can appear from the ringing or from the reflections.
Right. And so that's why you're exactly right. If we terminate the lines, if we're using controlled impedance, we terminate the lines, we don't have the reflections, we'll have the lowest amount of, we'll still have crosstalk, the lowest amount. Any reflections will change the signature a little bit. It doesn't change the amount of crosstalk. The amount of crosstalk is still about the coupling over here. It's what that crosstalk appears as because of all the reflections. So the mechanism, the thing you do to reduce the crosstalk is still about the coupling, but you want to pay attention to the reflections because that can only make things worse.
Okay.
There's one, sorry.
Yeah, go ahead.
There's one other complication that makes it a little difficult to interpret the behavior a little bit, and that's we've been looking at the case when the interconnects are electrically long. In other words, we've got this edge that's short, the spatial extent of the edge is short compared to the signal, compared to the length of the interconnects, and so we can watch that edge as it moves and its interactions along the way. When the rise time is long compared to the time delay of the interconnect, then we still have the same effects, but the rise time kind of smears out the behavior of the near and the far end crosstalk a little bit. It's not as clear and succinct. That means that we will always, when we have a longer rise time, the crosstalk, far end crosstalk especially, will always get less in magnitude. And that's why I think it was in your video, your tip number 1. Didn't you say in your tip number 1, use as long a rise time as you can for your signals?
Yeah.
Did you say that?
It's if you can, then slow
If you can slow the edge down, you want to do it. Because one reason is that will always reduce far end crosstalk. And sometimes if you make the rise time long enough or the interconnect short enough, it will decrease the amount of near end crosstalk as well. And so that's the second complication that makes it a little difficult to interpret the voltage that you measure at the ends. But if you have sub-nanosecond edges and you have interconnects that are a couple inches long, you will see a different signature at the near end than the far end. The dynamic nature of that signal is really important, influencing the behavior of the crosstalk.
Okay. I don't know how much time we still have because
I only have a minute or two here, but we can reconvene another time.
Okay,
this
so
is a core
last
dump.
question.
Everything I know about crosstalk, I've just told you now.
How fast or how it depends, or when we exactly get the maximum or the saturation of the what is the factor what influence this when you get the maximum?
Okay, so we're talking about far end crosstalk?
Yes.
Then okay. So I can show you unfortunately, you know the most common answer to all signal integrity questions?
It depends.
It depends, right?
That's not the answer what we are looking for. You like to be more specific.
The way you answer it depends questions is you have to put in the numbers. And so I have an example here, I think. I'm going to go back to the slides here. I have an example here of putting in the numbers. Because here is how we calculate the amount of far end crosstalk. This is that ratio of the voltage we see on the victim line at the far end compared to the voltage we see here at the far end on the victim line compared to the voltage that we're launching on the aggressor. We call that ratio the far end crosstalk coefficient. So it literally is a percentage. And you're asking the question, when is this 50%? Well, here's what it depends on. There's a term here that's about the coupling of electric and magnetic fields. That's where there's no good approximations. You have to use a 2D field solver to estimate what that far end coupling coefficient is. But it scales with the coupling length and inverse with the rise time. And so I've got here, so this is the far end crosstalk coefficient. I've got here, I did this for you. I took 50 ohm, two 50 ohm transmission lines. That defines the aspect ratio of signal to line width to dielectric thickness in microstrip. And I'm plotting here the separation in line widths because it's easy to see when you're doing the layout. But that's assuming you got 50 ohm lines. This is that coupling coefficient. This is that coefficient over here when you use units of length in inches, rise time in nanoseconds. So for example, when the separation equals the line width, which is tightly coupled. I see this in a lot of boards when you're routing dense buses on the surface. The coupling coefficient is 0.005. So you put in 0.005, and here's the length over the rise time. If the rise, and I put in some numbers over here. If you got let's look at this first one. If the length is 10 inches long, and the rise time, this is DDR4 kind of numbers, rise time is 0.3 nanoseconds, and separation equals the line width, the coupling coefficient 0.005, you put in the numbers here. Here's 10 inches divided by 0.3 nanoseconds times 0.005, that's 17%. If you scale, when does it saturate? 17% is already too much. Noise budgets typically like 5%. 17%, you're screwed already. But if you made this longer than 10 inches, if you doubled it, you get 34%. If you tripled it, you get about 50%. So 30 inches long, 0.3 nanoseconds, you saturate. That's how you use this relation. The only way to get this curve here, unfortunately, is with a field solver. Mm-hmm. And a lot of Polar Instruments 2D field solver will do that. I think there may be some approximations out there. None of them are very good, but like the Saturn PCB tool will calculate the far end coupling coefficient, but it's not a very good approximation. So I would recommend, if you want an estimate for this term here, use the Polar tool. Okay. So that's how we estimate it. So
thank you very much, Eric.
Okay. Gave a lot of information in a short period of time. We can always come back and talk about details another time.
And that's everything for today's video. I need to say, I really love the animation. And together with Eric's explanation, I really hope this video will help at least some people to understand a little bit more about crosstalk. I still have many questions what I wanted to ask, just we didn't have enough time. So if you think we should create another video about this topic, leave comments. Okay, if you have any questions about crosstalk, or if you have any questions what you would like to ask Eric, leave comments. It would not be possible to create this video without Eric's help, so I would like to thank you very much to Eric for helping me to create this video. And also I would like to thank you very much to you for watching this video. If you like this video, don't forget to press like button. If you would like to see my future videos, don't forget to subscribe. I really hope you found this video interesting, and see you next time. Bye.